Good evening, everyone. We'll just give another minute for people to join. Okay, so just want to bring up this course calendar. So pretty much we finished all the assignments, homework, and labs. The only one it's still out there is the homework 4. And it's due this coming Sunday. So please just make sure that you finish the homework on time and submit that. We can still accept some late submissions for prior lab. So if you want to, submit some unfinished work, which I hope you can finish by this time. So please let me know and let the TA know. And of course, there will be some late penalty applied if you still want to submit the prior assignments. So I think by the end of this week, we'll finish. We'll have all your submissions, and I have instructed TA to finish the grading as soon as possible, but obviously it will take him some time to go through all the submissions, especially if there are late submissions. I don't have the most recent grades yet as of today. I expect the TA will send me updates later this week. So if you want to check your grades, you can expect some reply from me after this Friday. If you want to just check individually your grades. But I think the grades are posted on Blackboard, so you know where to find them. And today is our last class, so I would like to use today's time to review the topics that we covered from after the midterm exam. Just give me a second. There's still people waiting to join. For those who came in late, I was talking about the remaining homework 4. It's due this Sunday. And if you choose to submit prior assignments, you can still do that, but we'll have to apply late penalty on those late submissions. Please let me and also the TA know that if you plan to submit any assignments that's late. And I expect the TA will finish grading hopefully by mid next week. I'll check with him on that. Do you guys have any questions regarding the labs and homework submissions? Okay. The other thing I want to mention is about the course evaluation. So, typically as usual that we have a course evaluation form that if it is an in-person class, we will have that form distributed in the classroom. But given that we are teaching this course virtually, so I will post the form on Blackboard, and I strongly encourage you to fill out the form. You can print it out, fill out the form, and bring to campus if you happen to be on campus in the next few days or before the end of the semester. You can submit the form to the secretary at the department office, Ball Hall 301. You can also email to the secretary directly, and those forms should not be submitted to me or emailed to me. Just want to highlight that. I will send out an announcement regarding the course evaluation on Blackboard. I'll have more detailed instructions there, and I strongly encourage you to fill out that form. And I appreciate any feedbacks that you have. And those submissions will be anonymous, so you don't have to worry about that. And I won't be able to see the forms myself. Anything else? Right. So about the final exam, it will be in the same format as the midterm exam. So the exam questions will be given on Blackboard. So the exam will be given on Blackboard as we did for the midterm exam. The number of questions will be similar to the exam and the midterm exam, but there might be a couple of more questions. And the format, it will be the same. So you'll see multiple choice questions and also multiple answer questions. And now you should know the difference. For multiple choice questions, you choose 1 out of the 4. And for multiple answer questions, you may have more than 1 correct answer listed. And you choose the correct ones, but you should not choose any incorrect ones. And there will be short answers. There will be blanks for you to fill. So it's going to be very similar in terms of format to the midterm exam. Okay, any questions regarding the format? And
I have a quick question, Professor.
yes, please.
I'm not sure if you said this, but is this a cumulative or is it only material after the midterm?
Okay, good question. So the topics on the final exam will be on the topics that we covered after the midterm. So it's not a cumulative.
Okay, and what my memory's not good, but what lecture was it after the midterm?
So I will actually talk about that. So it's
okay. All right.
It's week 8 through 11.
All right, thank you.
Yeah. So that's in fact the content I will go over today to give you I try to cover the 4 or 5 weeks of class in these 2 hours. I'll try my best. We'll see. And the final exam is on Saturday. So it's on Saturday, December the 17th, and 6:30 to 9:30. It's going to be given through Blackboard like we had last time. And the exam time will be 2 hours. So from 6:30 to 8:30. So just plan accordingly. I know it's a Saturday, it's a weekend, but that's how the registrar's office scheduled the exams. So we have to abide by that. So during the exam, you are required to turn on your webcam. So please prepare your webcam. You can call in through your smartphone, but you just test out. If you don't have your camera on, we'll have to keep you out of the exam. Do you have any questions regarding the logistics about the final exam?
Yeah, Professor, I just wanted to clarify that you basically said that there will be more than 50 questions, right?
Yes, so I have not, fixed the questions yet, but I expect there will be a couple of more questions than midterm, but it's not going to be, many more. It's slightly more, but not many more, if that makes sense.
Yep, thank you.
And again, the questions will be marked for graduate student only if those questions are to be answered by grad students only. Okay, any other questions? Okay. Okay, so this is a one-page PDF file that I posted on Blackboard under week 14, which is for this week. So this is a outline for the coverage of the final exam. As I mentioned here, this is for reference only, should not be treated as exclusive list of the problems on the exam. But I can say that the questions will be coming from these chapters and the lectures. The reason I say chapters is because for the contents around these topics, during the lectures, I use the slides to explain these different topics and with examples, maybe some extended materials, but the core materials are coming from the textbook, at least for from week 8 through week 10, those top 4 topics. So that's why in each of these weeks, the topics, I list here the text. So which chapter that you need to locate and preferably read through the contents. So for example, week 8, that's where we covered embedded processors. And the lectures, some of them are kind of extending topics such as the digital signal processors. And those are largely based on one of the chapters in chapter 8. So I list these 14 pages, for example, in chapter 8. So those are the contents in a textbook you need to get yourself familiar with. You don't have to memorize it, because it's again an open book exam. You can refer to these PDF files and the lecture notes. But what's important is, as you probably realize, that you really need to understand the contents of these chapters in the textbook to some degree. And you need to be able to locate any specific topic if you want to get more information. So I think the bottom line is you need to at least read these chapters once or twice to know, where to find relevant information. If you never read this book, then you're going to be having troubles locating these different materials and trying to find answers during that 2-hour time frame. So I don't require you to memorize these contents, but I hope that you will take some time to read through these chapters to know what topics were covered and where, if that makes sense. For the slides, I think probably the best way to review is to review the recorded lectures. And for each of these weeks, I have some videos posted, because some of the videos are processed from this semester's recording. And in the later few weeks, like 10 and 11, I used the recordings from my previous semester's recording, which is essentially the same. Maybe I talked, more or less on some of them, but largely the topics are covered the same. So you won't see, you will be able to find all the relevant information that we talked about in the slides. So those are the kind of the for the from week 8 to week 9 on these 4 specific topics: embedded processors, memory architecture, multitasking and threads, and quantitative analysis. In addition, I spent some time talking about one example microcontroller, this AVR processor. And the contents regarding the AVR processor were split into 3 weeks. I think you can track this. So the slides are, if you go to week, I would say week 11, or week 10. So I have 2 different places for these slides that center around AVR processor. And in also the lectures, I talk about different aspects about this AVR processor, from this I/O, general purpose I/O, how do we use some language to accomplish a simple task, for example, turning on or off the LED. Also, we talk about timer and also the interrupts. So those are the things that we covered about this AVR processor. You should be able to get all these slides from the one that I posted in week 10 or 11. We can later go into to identify that. And the videos are also split into 3 different places, but you should easily be able to find them. Okay, so the next thing is about Lab 2 and Lab 3. Lab 2 and Lab 3 were due all after the midterm exam. And that's why the materials that covered in Lab 2 and Lab 3 will be part of the final exam. I had a few questions put on the midterm exam. You can see that as long as you finished Lab 2 and Lab 3, well, worked on lab 2 and lab 3 extensively, you should be able to answer all the questions I put there. Really, what we want you to understand is the hardware and software design for these 2 labs. The Arduino-based game controller, and now this motor control and LCD display. So those are the things that you should learn from working on these labs, either by yourself or with your teammates. So if you, so for example, in a team, if you work on these 2 labs within a team, you and your team members may each focus on one aspect of the design or debugging. It's a good time now you sit down and kind of teach each other what the things that you have your partners work on. So you know the whole picture, even though you yourself may only focus on one piece of the lab. Now it's a good time that you all work together to make sure that you all know each other's work, so that you will be able, you will be equipped to answer any questions about these labs. Okay, any questions? Okay, so this is the big picture. So in the next an hour and a half, I want to try to review most of the slides that I feel particularly interesting and important. I may not be able to cover every single slides that that we talked about in these weeks, but I'll try to cover some of them. And feel free to ask me questions during the review. Okay, so I'm not gonna change to full screen mode because I can see if there's any questions in the chat. So this is slides that I covered in week 8. So here we are talking about embedded processors. We began with some general concepts about processors, and then we spent some time talking about the signal processing processors, which is kind of a unique category in the embedded processor group. And then we talked a little bit about parallelism. So when we start talking about processors, we talk about instruction set architecture. I think this is a very important concept that you need to understand. In instruction set architecture, or ISA, is the view of machine as seen by the programmer. But the programmer actually we're talking about here is an assembly language programmer. If you're writing high-level language programs like C, Java, Python, you probably don't care or not aware about the details of instruction set architecture, because the compiler and the other interpreters take care of those details. But if you get low-level programming, such as assembly language programming, and you program those processors directly, you have to be aware or have to understand the instruction set or SA used by this particular processor. So it could be x86, could be ARM, could be MIPS. And for these different processors, the their programming language, assembly language is different, and the number of instructions will be different, and the addressing mode will be different. So a lot of things are different. Microarchitecture is one level beneath the instruction set architecture. This is not even seen by the programmer. So you wouldn't notice any difference if you are working with just x86 processors, even though these processors may employ different microarchitecture, because microarchitecture is the realization of the ISA, which could be different from generation to generation or from vendor to vendor. So can one ISA be realized using more than one microarchitecture? And the answer is yes. Just use Intel's processor as an example. You have a lot of Intel processors from older generations, newer generations. They all use the same instruction set, but their underneath microarchitecture are different. They have different depths of pipelining. They have different branch prediction, and a lot of things are different at microarchitecture level. About ISA variety, I think this is where, particularly for embedded processors, there are a lot of specific embedded application specific instruction set or instructions. For example, digital signal processing, or encryption, or audio processing, FFT. So those could be added as a special function through these special instructions. So microcontrollers, in our discussion, we focus on the system on chip microcontrollers. So you have a CPU or data path, you have on-chip memory, some could be volatile, some could be non-volatile, and you have different functions on the CPU, on the processor, timers, even ADC or other functional units. And these microcontrollers are typically used in limited resource environment. They could have sleep mode, ultra low power mode to meet the application requirement. We talk about embedded signal processors or digital signal processors. This is where we kind of use a digital processor, which is called a DSP, digital signal processor, to process signals as if we are processing them using an analog circuit or other filtering functions. And so we talk about this example, this low pass filter that we characterize this circuit using their circuit frequency response, and also step response and impulse response. The concepts are a little bit complex if you didn't take DSP courses before. But eventually what we're doing here is that we want to use a digital processor to approximate such convolution function to kind of use the historical signal inputs to calculate the future output by following certain impulse response principle. So we take samples on the impulse response, and then we scale the samples, and then we kind of transform the continuous format of the convolution function into a discrete function. So we have this weights and also the input signals. We have a few samples of them, and this n could different from case to case, and eventually we're going to calculate the output voltage by using such a function. And when we implement this, we can plug in these factors and also use the corresponding input signal sampled to calculate this final value. So the filter structure is going to be implemented something like this within the processor. So we have the input signal, and there's delay functions to basically take timed samples from the input signals, and then use the factors or coefficient parameters and to do multiplication, pairwise multiplication. Then we accumulate them using addition functions, and then finally we get this output. So what we see is that using these approximation of this filter through this digitally samples and also accumulation functions, we can try to approximate the frequency response. It's not perfect because the precision and also because the number of samples we chose. But we're getting that trend. So what's important is that this FIR filter structure, which we've seen before, and this could be extended to n units. And the most important operation in this process is the multiplication accumulation altogether. And multiply is the function is applied from integers, and accumulation is going to be accumulate the product from this multiplication, and then finally we get the result. So what the digital signal processor is good at is to provide fast and efficient multiply accumulate, or MAC instruction. So this is one of the special instructions that could be found in embedded processors, especially embedded digital signal processors. And from the processor design, it typically includes a very large accumulator because the larger values coming from the multiplication. Also, in such processors, a Harvard memory access architecture is typically used. That means we have separate instruction and data, separate instruction memory and data memory. Also, it may have often have this auto increment addressing mode, so that you can get down to the next sample, which was stored continuously in the memory. Also, it supports circular buffer addressing, which is for delay of these input samples, and also support zero overhead loops. Okay, so eventually we have this digital processor that can be used as approximation to the analog filter to implement certain specific desired functions. And at the end, we talk about parallelism versus concurrency. And so this is a topic that I think is important. The way to understand this is that so both of them, meaning the fact that you have multiple tasks that are currently ongoing but not finished. But parallelism is more, or it has more stringent requirements in terms of the hardware support. So for parallelism, the tasks are said to be parallel, and they are physically executing simultaneously. So you literally have to have multiple processors, or at least multiple cores, to execute these different tasks. On the other hand, concurrent is kind of a softer requirement in a sense that you can still have concurrent tasks with one single core, one processor, because these tasks will time share the processor. So one task, execute a few instructions on the processor and then switch to another task. So they are conceptually executing simultaneously, but not necessarily at exact moment. So this is the concurrent. Yeah, so nowadays you see more often multi-core processors, and the multi-core processors is good at kind of improving the system's throughput. So when you have 2 cores or 8 cores or more, you not necessarily these processors can not necessarily speed up a single task. That's often not their goal. Rather, the goal for these multi-core processors is to improve this processing throughput. That means they can get not only one task, but maybe 4 or 8 tasks done at the same time. So you can have more tasks going through the process, and you finish more tasks at unit time. So that's the point I want to make here. All right, so any questions about this one? All right, so I'm gonna switch to memory architecture. Okay, so memory architecture. So we want to talk about the roles of memory and memory organization for programs. Remember we mentioned the hardware architecture, the Newman architecture, and also here in this topic we talk about the cache, which I think is important for you to understand. Okay, so here are the things we talked about in this part of the slide, this part of the class. We talked about types of memory, volatile versus non-volatile, SRAM, DRAM, and we talked about memory maps, hardware architecture, memory map I/O, and we talked about memory allocation, statically allocated stacks and heaps, memory model of C, and caches. So these are very classical concept: non-volatile memory, volatile memory. I think what you need to understand is flash memory is non-volatile memory, and the earlier kind of form in EEPROM or EEPROM. You still have these. But these are kind of the earlier format of this flash memory. Flash memory, of course, it's I should say the application of these different types of non-volatile memory is quite different. For EEPROM and EEPROM, you don't expect to write to them. You could write to them once at the beginning, but the rest of the time they are used as read-only. Whereas for flash memory, you do expect to write to the memory besides reading from it quite often. Reading speed is fast, but writing to flash memory is slow because you have to erase a block in order to write a new content. Also, the kind of the lifetime is limited. Depends on how long you want to use it. You may not find out, okay, this flash memory can sustain 1,000 or 10,000 programming erase cycles. But if you have a flash memory that let's say you have a memory stick that you use quite often, store games or pictures. And you may find out after a year or two, that flash memory just basically gone because the life cycle reaches the limit. Volatile memory it includes SRAM and DRAM. The difference is that SRAM is faster but more power hungry and less dense. So how do I understand this density? Less dense means that using the same number of transistors, you could store fewer bits in SRAM than in DRAM, because in order to store 1 bit in SRAM, you actually need a lot more transistors than in DRAM. But on the other hand, DRAM is slower, and also its access time is not constant. It depends on the sequence of addresses, and also it requires refreshing. So DRAM is slower than SRAM, although it can be of larger capacity. Okay, this is the memory map architecture. Just don't take these numbers literally. So these numbers could change from processor to processor. What we want to show here is that for a memory address space, as you see this one, when we talk about a memory address space, it starts from 0 and all the way to the maximal address. So this is the address space for this processor, which you can see it's about 4 gigabytes. So that's a 32-bit address. And we notice that we have A, B, C, D, E, F, G, and these several segments or regions that we carved out and allocate them for specific device or devices. This first section is program memory, and the type of storage is flash, followed by data memory, where we use SRAM, and then followed by peripherals, and these are memory mapped registers. So the way to understand this is that these addresses are possibly coming from the microprocessor to access. But really, what hardware device, memory or I/O device or other things, what components provide data for microprocessor depends on what type of devices you allocate this memory address to. So for example, the first half gigabytes of this memory address space, this is allocated for program memory. And for program memory, for this particular processor, we use flash. So whenever the processor access will try to ask information within this address range, that address will be decoded by this flash, and then hopefully the microprocessor will read that instruction from this region. And the same processor, if it issues the address for between this 20000 and this basically the next half gigabytes, if the address falls in this range, then that address will be sent over to SRAM. I should not say sent over, it's in fact decoded. There's a decoder circuitry so that this data memory implemented in SRAM understands what exactly the microprocessor is requesting. So this is a good example to show that for the whole memory address space, the microprocessor and the whole system designer can decide which part of the address is mapped to what function, to what component in the system. All right. Okay, so this is the Mega 168. This is the 8-bit microcontroller with a 16-bit address. So why do we call a microcontroller is 8-bit or 16-bit or 32-bit? It is because the size of the ALU. So this 8-bit processor, that means for the ALU, for each input is 8-bit, and the output is also 8-bit, maybe a carry bit as well. So, and that's the reason a processor is called a 8-bit or 16-bit or 32-bit. processor. For this particular processor, it has a 16-bit address. So 16-bit address means that for storage, for finding data in a data memory, we are using 16-bit address. Even though for each location here is an 8-bit register or 8-bit information. So this is the data memory map, and it starts from address 0 going up. Well, it depends on how you draw it. This is going down, but in terms of the address range, it's from 0 to the maximum address. And the reason you see 3 numbers here, it is because for this Mega 168 processor, it has 3 different variants. So the largest address is different. And in this memory map, so we have the first 32 bytes are for 32 registers, each 8-bit. It's a 1-byte register. And then followed by 64 IO registers. And so that's has the address from 20 to 5F in hexadecimal. Then we have some extended IO registers. Then beyond address 100 in hexadecimal, we have the internal SRAM. So this is how we can read these memory maps. What do we mean by that? And also you can see that this is a typical system on chip. We have general purpose registers feeding to ALU. We have SRAM, EEPROM, and we have flash memory to store programs. And in addition, we have interrupt units, SPI, watchdog timer, analog comparator in IO modules. Okay, so what is the difference between 8-bit microcontroller and 32-bit microcontroller? It's because of the data width of the ALU. Why use volatile memory? Why not use non-volatile memory? Because in computation, volatile memory reads and writes faster than non-volatile memory. So you need some amount of non-volatile memory at runtime. Okay, so we spent quite some time talking about statically allocated memory, stack, and also heap. So these are different ways to organize your variables, program in these different memory, and these memory are managed differently. For statically allocated memory, the compiler chooses the address at which to store a variable. Stack is dynamically allocated within memory using a last in, first out strategy, or first in, last out, depending on how you say it. A lot of the function calls that will have to rely on this stack to maintain the information that can be carried through these function calls. Heap is another beast. This is a totally different way to allocate, especially big chunk of memory, and it's typically managed by an operating system. All right, so next few slides, we talked about examples of statically allocated memory. So for example, this one, we declare this variable X outside the main. I'm using a C program as an example. So this variable X is character type, and this is basically 8-bit data type. And in the main program, we basically assign 20 to this variable. Because we declare this variable outside of the main and also, in fact, outside of any function, so this variable is accessible to all the procedures, all the functions. And so its lifetime is the total duration of the program execution. And this is the perfect example of a statically allocated memory, because you want that variable, you want the value to be there all the time, always. So this is also a way to declare a statically allocated memory. We can declare this character type of variable data type variable X, and also we can add the static keyword before that. This is to say that we want this variable X to be allocated in statically allocated memory, as we did in the previous example. However, we only want this full function to access this variable. That's how you can implement using this static keyword. Okay, so for any variables that you declare within a function, like in this example, this X, which is of character type, it's declared within this full function. This is a good example of automatic variable. This kind of variables are allocated on the stack, and they're only allocated when this function is called. And when this function finishes, and the memory space taken by this variable X will be reclaimed. And the way to implement that is to use a stack pointer, which I didn't show here, but you can think about there's a pointer pointing to the top of stack, and when in this case the stack pointer moves lower memory address when you get called, so you're basically moving this pointer to upwards to the lower address, and with that you have one more room, or however number of bytes you need to store these automatic variables declared within this function. And once this this function call is completed, then these variables will be kind of released. And the way to release the space is that by incrementing the stack pointer. So it grows backwards, so that whatever space that was allocated at the time when we enter this function is now going to be reclaimed. Okay, so the first, so I have a few questions regarding this allocation of the variables. The first question here, what does it mean by the following code? We have a character type of data X, this variable X, and in this full function, we assign 20 to X. Well, I have answers on all the slides, but what we are showing here is that this variable X is kind of statically allocated variable, and it's is allocated in the SRAM determined by the compiler. So you can expect the compiler will find a location here in this region. And so this location that's chosen by the compiler, and when we call this full function, the processor will put this 20 in hexadecimal to that location. So this hex value 20 will be stored at this assigned location. Okay, next example is very similar, but now we have an asterisk. So I have a star here. And you know that in C code, when you have this asterisk in front of a variable, and this variable becomes a pointer, and it points to a 8-bit value because this character, this is 8-bit value. So X is a variable, but now it's a pointer to a 8-bit character, 8-bit value. So what does it mean by this? And again, in this full function, we'll assign 20 to X. So because this particular processor, this is still the Mega 168, it has 8-bit data path, but 16-bit address. So because X is an address, because this is how we declare it. So X is a 16-bit quantity. Okay, it's a 16-bit quantity, and this 16-bit quantity is stored statically in a statically allocated memory because we declare this X variable outside of any function calls. So this is a, we call, I think in C called a global variable, and this variable X is a statically allocated quantity or variable. And because we assign 20 to this, so we actually have a 16-bit value called 0020. And that's the result of we assign this X to 20. So this X itself is stored here using actually 2 slots or 2 bytes because it itself is a 16-bit quantity. But it actually points to address 20. And so that's here. So that's the beginning of the IO register. Okay. Okay. So I have a few more examples after this slide, and I highly encourage you to review these examples and make sure that you understand, why, how, what do we mean when we declare a X or Y as character type, and some of them, like X here, we have a heuristic, and what does it mean by that, and what's the assignment is for. So I think it's a good. You will find your time well spent when you go through these slides and understand the in and out. Do you guys have any specific questions about these examples?
Will these slides with the answers be posted to Blackboard?
It's already there, I think. Yeah, I'm pretty sure
Okay.
it's already there. Yeah.
Thank you.
Yeah, so this is 9, so this should be in week 9 folder. Okay, so it's 7:28 now. Let's see, let me finish this set, then we take a break, and then we, after break, we'll continue on the other materials. Okay, let's see. Okay, recursion. Well, I think, well, recursion is where you call the same function within the function itself. So it's not a good practice in embedded programming. It's just, I would say this example is purely a mental game for you to try to see what's going on. But in practice, you rarely use recursions in embedded programs. Okay, so we talked about static allocated memory, and we talked about stack. Heap is another kind. Heap is to offer a way to allocate a chunk of memory. And this area that we allocate the memory from is called a heap. And in typical scenario, you will use malloc to allocate this however number of bytes in this heap, and then use free after you finish using them. If you don't use these malloc and free properly, you end up having memory leaks or memory fragmentation. Memory leaks is where you for example, if you malloc, but you forgot to free the same location, then eventually you will run out of memory. Memory fragmentation may not happen, depends on what kind of malloc and free procedures, what sequence you have. The reason being that when you do allocation and then free, you basically taking pieces or taking chunks from that contiguous memory region. And depends on what's the size you alloc and how much you free and what time. You may have little, fragments of these free memory scattered around. So altogether, you may add up. Let's say you may have 100 megabytes of free space if you add these tiny fragments together. But you cannot allocate a contiguous, 50 megabytes of space, because all these are, spread out. You have no room to allocate a contiguous, 50 megabytes or even 10 megabytes. So that's the memory fragmentation problem. And so correspondingly, there are solutions such as garbage collection will often, carry out these rearranging the previous allocate memory so that the free space will be also contiguous. And but moving these segments around, that means copying data from one place to another place to make room for a contiguous region. That's costly. And that's why it said it's deadly for real-time programs. You don't want that to happen. You know what? Let's take a break. It's 7:32. We'll take a shorter break. We'll reconvene at 7:40. All right, let's continue. So the second part of this memory architecture is about memory hierarchies. In particular, we're going to talk about the cache. Cache and scratchpad are both ways to speed up data access. But cache is a subset of memory that's mapped to SRAM. Let me explain this way. So cache and scratchpad are both based on SRAM. But the data that you find in cache is a subset of data that's stored in the main memory, the DRAM. Whereas scratchpad and DRAM have different memory address space. So there's a separate, so the data in scratchpad may not be in DRAM. We didn't talk about segmentation, so you can ignore this part. So cache sits in between CPU and main memory. Really, the CPU and the cache is on the same chip, and main memory is off the chip. So from cache to memory, processor to main memory, this is a slower access than CPU accessing the cache. So really, we want to have data. We want the CPU to find data, either read or write, in cache. If that's the case, then CPU do not have to go to the main memory to read data or write data to. That's the reason that we want to take advantage of the cache as much as possible. If the CPU can find most of its data in a cache, then that's a good news. That means CPU does not need to go to the main memory, which takes much longer time. But because cache is much smaller in terms of capacity than the main memory, only a small subset of the data can be put here. So based on how this cache is organized, you may be able to store data in location A versus data in location B. Sometimes you cannot store both of them if they happen to be mapped to the same cache line. So cache line is a concept that we used later. Cache line refers to cache blocks. So every time we bring data from the main memory to the cache, we bring the whole block or whole cache line, which typically could be 64 bytes or 128 bytes. Let's see. Yeah, so this is about that. Whereas scratchpad, as you can see, this is in parallel with the main memory. Whereas in the last case, the cache is part of the main memory. It's a mirror or keep copies of subset of the main memory. Whereas scratchpad and main memory, these are two separate things. They have separate address space. So you find address from 0 to the maximum address, main memory starting from 0 to the highest address. Okay, so this is the direct mapped cache. This is the simplest cache. What we see here is this is the cache. This is where we keep copies of data in the main memory. And each set here has one block. And for each set, we have the actual data. we call the block or cache block. This is where we store those 2 to the power b bytes. So this could be 32 bytes, 64 bytes, or 128 bytes. It's all here. And then we have a tag. We'll explain what's that for. And then we have this valid bit. This valid bit is just simply 1 bit to mark whether the content in this block is valid or not. We need this valid bit because at the very beginning, when we have no valid data here, but we still have 0 and 1, some random bits here before we load the first copy into this block. So before we do that, we need to mark this as invalid, because at this time, if the processor wants to access this validation or validity bit, will indicate that these are garbage bits or bytes. When we have data copied into this block, loading from the main memory, that's when we will mark this as a valid. So next time, the processor can actually use this the data in this block if the address matches with the tag. Okay, so what we see here on the left side, this is the address coming from the microprocessor. So whenever the microprocessor needs to get something, read data from a table or write data to some other locations, it will use address to access the main memory. This address altogether has m bits. The lowest b bits, it happens to be the same as this b here, because this b bits decides how big the block is. So that's why these lower b bits are actually the block offset. So if we have 0, 0, 0, or 0 here, then we're talking about the 0 offset. If we have a 1, then we're talking about byte number 1. And if we have, let's say, 1, 0, 0, 0, so that's 8. So we have offset 8 here. All right. And then the next S bits, and that's set index. Because in this cache, we may have a number of sets, and could be 2 sets or 4 or 8. So we'll have, let's say if we have 8 sets, then we're talking about from 0 to 7. Okay. So for this 8 sets, we need 3 bits to identify which set that I need to inquire about. And the rest of the bits, the upper T bits, are used for tags. And this is the same number of bits as this T tag bits here. The reason being, you could have multiple blocks that could map to this location, this set, but you need to use the upper T bits from the address to compare with this tag bits stored together with the block to make sure that that's exactly the same block that the microprocessor is trying to access. If this is different, then even though the set matches to this set number, we still cannot use the bytes that's stored in this block. Okay. If we see a matched tag bits here, so these T bits are exactly the same as these T bits, and this valid is 1, that means it's a valid block, then that's what we call the cache hit. So that's when the microprocessor can use the bytes here in this block without needing to go to the main memory. And of course, the exact byte the microprocessor will access is determined by these offset bits. Okay, so this is how these direct map caches are organized. and how do we go from a address to the actual byte by using this set number and tags. Okay, and this set associative cache is a little bit different in the sense that for each set, you may have more than one block. And in that case, after you go to that set using these bits here, there are a few different blocks you need to compare with. You need to compare these tag bits from the address with all the tag bits to see if there's a match. The reason that we have this set associative design is to allow multiple blocks to be put here to reduce conflicts, but at the same time, it make the tag comparison a little bit more complex, because now you need to compare with 2, 4, or 8 or more tags at the same time. Okay. All right, so that's about the memory architecture. Do you have any questions? Okay, let me move on to the next one. Okay, so in multitasking, we focused on threads, and also we talked about typical problems of thread programming. There's several things that unique about threads. Threads are sequential procedures that share memory. Threads are different from processes. Processes, they don't share memory, but threads share memory. And they can exploit the parallelism hardware, and they create illusions of simultaneously running programs. They can be efficient to handle software interrupts and or reacting to external events. Thread scheduling is kind of a wild place. Different operating systems may schedule them differently. So that's why you cannot, have this assumption or any assumption of a particular thread is going to execute before another one, unless you provide specific semantics like logs. So overall, thread scheduling is not a universally determined policy across different OS. They come with a lot of complications, complex situations. POSIX threads is one type of threads. It's kind of universal in Linux or Linux variants. It's a library of C procedures. We use this simple multi-threaded C program as a start, to illustrate what it takes to create threads and how to define thread functions and how to make sure that concludes nicely or as expected. This is a way or typical way to define a thread function for P threads. The function prototype, it returns null pointer and also takes a null pointer as an input argument. You can do, all the things you want in as you plan in this thread function. In the place where you create these threads, typically in the main function, you declare thread identifiers and use these identifiers as one of the arguments to this pthread create API call. Pthread create is an API call from the pthread library. It takes the thread ID as the first argument, then some options that you can define. We typically choose null here to choose all the default parameters for creating the thread. For example, priority, things like that. You don't have to specify any, so that oftentimes you put a null here. And the third argument is the thread function. In our case, we have this print n that we defined earlier. And then lastly, that's the input argument that you want to pass into this thread function. So in this case, we chose to use these two variables that we declared in the main function, x1 and x2, respectively, for these thread 1 and thread 2. And pthread create only, create the thread, but it does not mean that the thread will be executed right away. It could be, but there's no guarantee that. So even though you create these thread 1 and thread 2 in such a sequence, there's no guarantee that thread 2 is going to be executed after thread 1. And the order could be exactly the opposite. And when this thread executes, and because these two threads are concurrent, that means they are both active. They have not finished yet. So they will print out their IDs because of this for loop. And could be random sequences. Maybe my ID 1 will print it 10 times before my ID 2 will print it 10 times, or vice versa. Or even worse, you may have these my ID 1, my ID 2 printed inter-leave. So there's no guarantee how these threads are executed. And that's another example of the thread scheduling is not a kind of done deal unless you put any other API calls to enforce their orders. And because these threads are executing and because we pass in this local variable, automatic variable, x1 and 2, x2, and we don't want thread to main thread to exit before these two threads complete. And so that's why we have this line 17 and line 18 where we call pthread join. These two API calls, or this pthread join API, will take the thread ID as the first input argument, then the status as the second argument to basically wait for that thread to finish and also capture the return result. So with these two pthread join, the main thread, the main function actually waits for both P1 and P2, pthread 1 and pthread 2 to finish before it goes to line 19. All right, so we mentioned a few things, important things. The thread function template has to be like this. And we use pthread to create a thread and also pthread join to wait for that thread to finish. we can pass in input arguments and all to the thread function or capture the return from the thread function. So again, following this slide, there are a few slides with examples to show where the thread creation could go wrong, especially when you work with variables that are created locally or automatic variables. In this example, where we have, the same thing as we saw earlier, we have a main function where we have a pthread create function to create this thread and then join, and then we print the return value and so on. And then this thread function, we have a my thread. The name of the function is my thread. And in the function, we have 2 lines. We declare a local variable, automatic variable called RET. We assign the value 42, and we return that the pointer to the variable. And then in the main function, we use pthread join to basically wait for this thread to finish. So basically wait for these 2 lines to finish. And then we capture the return value, which is the pointer to the local variable RET. And then after that, we print a number by dereferencing that pointer we return. So by first look that you may imagine that, okay, so we'll get the pointer to this 42, and then we will then dereference that pointer, like reference the pointer, and then we expect to print a 42 and then finish. But as you see that we know in the second slide, in the following slide, that there's an issue with this example. Actually, more than one problem. Firstly, this you need to have a input argument, and which is not there, so that will cause issues. The bigger problem is that this pointer is pointing to a automatic variable or local variable, which was allocated on the stack. Within this thread function, this RET is valid, so the pointer is valid. But when you return or when you finish this thread function, that variable, the location that we use to store the variable on the stack, is now be deallocated. So even though you can pass the exact pointer value through this pthread join back to the main program, so you think that, okay, status now has the pointer to the RET, but because that space in the stack here may just be, this is, once this thread finishes, we are back to this point, this location may be filled by other function calls. So there's no guarantee that you will still see a 42 stored in this exact location, because other function calls may happen and other values may overwrite to this location. Okay, so I think this is a very good example that I strongly encourage you to look into this further to understand what is the problem, and so that you, in the future, you don't make the same mistake. I think the main concept here in this example is the automatic variable, which is dynamically allocated on the stack. And once the function finishes, that space will be reclaimed. So any pointer to that location will may not give you the value you intended to access. I have another example, which I don't want to talk about. You can. There's notes here, and I think you should refer to the prior recordings. Okay, so all right. So the next, I think, around 15 slides are about the problem in thread programming. The problem really is the accessing shared variables. When you have multiple threads that share variables, each one of them may make changes. Okay, yeah, anyone in the waiting room, I already let them in, so. Where was I? Right, so when multiple threads trying to access shared locations, the order of their access may affect the correctness of the result. And one important thing, one challenge is how do we make sure that the access will be ordered in such a way that you will guarantee a correct result. So one example we have here is the observer pattern in C, where you have a kind of one-to-many dependency between a subject object and any number of observers object, so that the object subject changes state, all its observer objects are notified and updated automatically. So it's a bit long, it's a little bit convoluted, but really the example here is a linked list that we try to update, and from that linked list we will supposed to find the function calls, and then with that new changes, updates to the parameters, we want to make these function calls. So we have this notifier procedure, and we have a element kind of list of listeners. We're trying to use add listener and to grow the linked list. And when we call this update, we will basically go through the nodes on the linked list, where in each of the node we have a function call to be called using this updated value. So this is where we have some details. This is to declare a element. This is essentially the node on the linked list. As you see that we have a pointer that you will use to chain these nodes together, and each of the node has a listener function, which is a kind of a function pointer that we will call using the update value here. Right, this is the procedure to add a listener to the list, and it differentiates whether the linked list is empty. If at the beginning there's no node, then in that case we'll create a head node, and we'll have the tail pointing to the head node. If the linked list has already some elements, then we will allocate a new node at the tail, move the tail to the latest one, and add the listener, and then also mark the end of the tail. This is where things get very tricky and causing problems when multiple threads are trying to go through these steps, because each of these lines could be executed by two different threads. So if two threads are trying to do this line at the same time before they finish everything, what end up having is that they will use the same tail and create two new nodes, but in reality, only one of them will be linked on. So this is, you want to, this is where you want to, write down on a piece of paper to see, okay, how this add listener procedure is trying to grow the linked list, and give yourself, draw on the piece of paper that to see if you are what will happen if two threads trying to execute this same line at the same time without completing the rest. So in that case, two of these threads will use the same tail pointer, and they will malloc on each side, but the tail pointer, the next can only point to one of them. So essentially, the other, the new nodes allocated by the other thread will be essentially, lost because you have no way to track it. Same thing is when you execute the next several lines, depends on which thread that you are executing this, you may end up linking to an incorrect node or adding this listener to a one that's already there. I would say you overwrite some of the listener function pointers. What else? Right, so this is the well, I was trying to explain will this work, and the answer is no, and what will be the unexpected, undesirable behaviors. So this is something that I want you to hopefully can draw on a piece of paper, just trying to imagine two threads are trying to execute this part. So this problem is what we call a race condition. This is where the concurrent code accessing the same resource, which is the tail pointer. Okay, so what do we have to do to resolve this? We could add locks. We could use pthread mutex lock. Mutex stands for mutual exclusion. So we have lock and unlock to guard these regions. For example, if we add a lock at the beginning of the listener and unlock at the end of the listener, we can somehow reduce the problem to guarantee that adding a new node will be correct. But because these locks are accessed on two different occasions, and if there's other places, for example, if this is where the element listener, this is the function call to basically print out or display a new value on the monitor for the pilots. So this is another function. You don't know if this function is going to be complete quickly, or if this function will require another lock. So that's where the deadlock risk will be significant, because if this listener function is stuck, then you will not unlock. So this mutex lock, this API will never get passed. So this add listener function will be stalled. Okay. So the thread programming is very challenging, and the accessing the same memory is the kind of the root cause of it, because from the perspective of any thread, the entire state of the universe can change between any two atomic actions. And you really have to be very careful when you program threads. On one hand, you want to utilize the resources, different cores, to make your program more efficient, but at the same time, you may introduce any potential risks of deadlocks. So there's alternatives to use send and receive or message passing, but still there could be risks of deadlock. Because eventually for send and receive, you use mutex and those PV operations to handle an internal queue between the send function and the get function. So you may end up having deadlock risks as well. All right, so followed by that, I have presented some kind of theoretical, more formal, well, I shouldn't say formal, more abstract analysis. We view this computation as changing bits. So for one computation, let's say for one instruction is to change from one bit sequence to another bit sequence. And we can have composition of computations, and that means you can have a series of instructions like you have a program. So the programs really to specify the compositions of computations, i.e., a group of instructions. And in a single-threaded environment, you expect that these sequences will change the initial state of a bit sequence to another state and eventually to the final state. But because of multi-threading, what you end up having is that for any thread that's executed, this thread may change the state. So before this blue thread resumes, well, before at the very beginning that it has assumption that it sees bit sequence Bn, but because of this new thread, so that Bn may change to B prime. So when the blue thread resumes execution, it sees differently. It's not Bn anymore, it's now B prime. And then, of course, the thread will have no idea that this is the case. So it will continue its execution, and at the end, unfortunately, it will cause an incorrect result. So given related back to the add listener example, so this another thread changes the value of tail or tail next, whereas the original thread has no idea that the new tail has been updated or being updated, in fact. So that's where you may end up having two tail pointers pointing to different locations, or one thread allocates space, but that space, the new node got disconnected from the linked list. All right, so that's the multi-threading. Do you guys have any questions? Okay, so next part is the quantitative analysis. Okay. So we talked about why do we need quantitative analysis, because a lot of the applications are time critical. It's a determining factor for safety, security, and also for those power constrained devices. You want to make sure that you can accomplish the task within given time. So time is critical and central to cyber physical systems. And we focus on worst case execution time. There are also analysis on the distribution of execution times. So what is the probability of this execution time is less than 100 milliseconds, for example, or threshold? And can you produce a test case that cause a program to violate its deadline? So there are different timing analysis problems, but we are focusing on the worst case execution time, which represents the longest time taken by a software task to execute, given the input data and environment conditions. Also, on the other hand, we have the concept of best case execution time. Okay, so why is it important? Because it's central to several physical system needed for correctness and performance. Can worst case action be always be found? It's in general, no, because the input data could be different. The running platform could be different. But in many cases, we assume we only focus on a segment of the program, and also most of the time we assume there's no effect from the caching, or there's no cache. So you could use some of the techniques to kind of try to get a good understanding of the worst case execution time. Okay. Right, so we use this example. So this is a modular exponentiation calculation. The actual computation is not that important, but what we want to show here in this example is that we have a few lines with simple statements, assignment statements. Also, we have this while loop. So this is a loop with the loop iteration variable I, and we update I every loop iteration, and we'll end the loop when condition is held. When in this particular example, because we know the value of I, and so we know how many times this loop will terminate. And we use this simple program to illustrate how we analyze this part of the code using control flow graph or control flow graph. We use these boxes to capture those basic blocks. Again, for basic blocks is where we only have a one entry point and one output point. I should say there's only one exit point, because some of blocks you have more than one entry point. Except those condition checking. For all other ones, you have one exit point. So all the instructions will be executed together. So if either none of them is executed, or all of the instructions are executed. All right, so use this control flow graph. We can come up with ways to analyze the longest path, finding the loop bounds, and identify feasible paths. And then another approach is to analyze processor behavior using instrumentation and measurement instructions. We'll talk about later. We did some examples about path explosion analysis, or for example, in this example, we have nested for loops. We have two levels, for loops. And in the innermost loop, we have a if else statement. So essentially we have two paths here. And then after that, we have a few instructions. Those are going to be in one basic block after the for loop. So the question is how many paths we have in this example. So first of all, we have two nested for loops, and the maximum iteration per loop is 100. So now we have two levels. So altogether we have 1,000 iterations of this innermost loop. And in the innermost loop, we have two branches, right? There's two paths, either this path or this path. So as a result, we could potentially have 2 to the power of 10,000 paths, because it depends on which way you go, and you have 10,000 of these possibilities. So that would be 2, times 2 for 10,000 times. That's why it's 2 to the 10,000 power of 10,000. For loop bounds analysis, we you show here this example because we know I is a constant number 32, and that's the maximum iteration. That defines the maximum number of iterations 32. Okay, so next we used a approach called control flow graph analysis to come up with a set of constraints which can help us to understand the worst case execution time. So what we do here is we use the control flow graph to, in addition, we label those basic blocks, the number of times a basic block is executed, and the number of times a edges is executed. So we have a graph annotated like this way. And then based on the control flow, we can come up with a set of constraints. For example, this x1 is equals d1 d2 is because this entry point is this incoming edge and this outgoing edge, and this x1 will be identical. So how many times this d1 is executed will be how many times this whole block is executed, and it will be how many times this outgoing edge is executed. So that's why this d1 equals to x1, d equals x2. And then we have this x2 equals d2 plus d4, which means that because we have two entry points for this loop condition checking, d2 is from the basic block b1, and then this is from basic block b3. So this edge plus this d2 will be the number of times x2 is executed. Likewise, x2 is equal to d5 plus d3. So in this way, we can come up with these constraints, and our goal is to maximize this summation of these products. Each term in the summation is the execution time of the basic block I times the number of times the basic block I is executed. So this is the execution time of this basic block I, and we add them together. All right, so this becomes a linear, integer linear programming problem, even though it's NP hard, but there are good software to do the solution finding, so you can solve this. And then that will give us a solution of xi, and then with x this coefficient x, or you can think about coefficient or the number of times the basic blocks executed, the x1, x2 up to xi, then we'll have we'll be able to calculate this. All right. Yeah. So adding when you have two parts of for a task, if you find the worst case execution time of these individual parts, you cannot simply add them to come up with the overall worst case execution time. All right, so this part, I probably gonna spend, yeah, let me talk about this part. So processor behavior analysis, cache effects. This is where we kind of link the things we talk about the cache with these processor behavior. Let's say this in this function call dot product, we are going to do element-wise multiplication and then accumulation on two floating point arrays, X and Y. And we have a for loop to do that. Suppose we have a directly mapped cache with two sets. Each set holds 4 floating point numbers. And X, Y stored contiguously, starting at address 0. So when n is 2, that means we have 2 elements in X and 2 elements in Y. And because they are stored contiguously, so the 2 floating point numbers in X and those 2 floating point numbers in Y are actually stored within one cache block. Okay, if you think about the cache, and each set we have a block, and in a block we happen to save 4 floating point numbers, and because n is 2, so we have both X and Y, those two arrays, total 4 floating point numbers stored in the same cache block. So when we execute this line, because we have to access X0, when we bring in X0, the cache actually brings in the whole block. And guess what? X1 is there, X0 is there, Y0 is there, and Y1 is there already. So when the calculation, when the microprocessor needs the calculation, it will have a, wait a minute, I have that. Yeah. Maybe I should use this one. So what I mean by that is we have this block, which stores can store up to 4 floating point numbers. And so we have X0, X1, Y0, Y1 already here, because the way the whole block is loaded from memory. The first access, which is to X0, will be a cache miss because at that point nothing is here yet. And then the following access to X1, Y0, and Y1 will be a cache hits. Okay, so overall, what will happen is X0 will be a cache miss. So the microprocessor gonna ask the cache to pull in the whole block, which contains X0, X1, Y0, and Y1. So all the rest access cache hits. Okay, but then things are gonna be different when n is 8, because when n is 8, we're talking about 8 floating point numbers in this array X, and another 8 floating point numbers in array Y. And we cannot hold all of them. So we're going to pull into X0 through 3. But when we access Y0, it's not there in the block, so we'll have to pull in Y0 and Y through Y3, all the 4 floating point numbers, into the same set. And that's the problem. And that evicts X0 to 3. So every access will have to bring the new data and then kick out the ones already there. So which means that you're going to be loading new data all the time due to the cache miss all the time. Any questions? Okay. All right, so I want to Yeah, I think you want to here's that. Not this one. Yeah, so the next few slides about measured time on a processor. That there are different ways. One is to use the instrumentation instructions on CPU to read the processor cycle counter and then calculate the time. Whereas other ways are different. This one is to use a simulator, which may not be available. And this is using analyzer equipment. It's more accurate, but the setup is more complicated. Instrumentation will incur overhead, so you want to run the code longer by repeating the code that you wanted to measure. That will compensate the overhead. What I mean by that, for example, if the code that you measure is like in the millisecond or even microsecond level, and you're going to take maybe hundreds of microseconds to add these special instructions to read the CPU counters, then the actual measured cycle counter will not be as accurate, because your measurement target is already very small and your overhead is at the same scale. So what you need to do is to repeat the code that you wanted to measure, let's say for hundreds or thousands of times, make your measurement longer. So the overhead you spend on these instrumentation instructions are going to be negligible. What kind of instrumentation instructions? So these are the ones. For example, set up the counter, access counter, and using this read timestamp instructions to read the CPU cycle counts into these registers, and then do the subtraction. So those are the overheads that you have to spend in order to use these instrumentation instructions. Okay, so that's the things I want to talk about. The execution time analysis. Do you guys have any questions? Okay. All right, what's next? Yeah, AVR processor. By the way, so the materials that I covered about the networking and IoT, that was before Thanksgiving break. So that's not going to be on the exam. So that's why I didn't even include those topics in the review guideline. Let me show you again here. And so the materials I covered in week 12 about networking, those are not going to be on the exam. All right. Yeah, AVR process. Okay, AVR processor. We talk about AVR processor architecture. There's AVR processors are kind of one good categories of processors with AVR instruction set used in many of those embedded systems. It has been there for a while. It's not the most expensive one, but all the things we covered can I think the the way to understand these processors can be applied to many other processors with different instruction set. We talk about I/O, and then we talk about the timer, and we talk about interrupts. This is the system architecture. As you can see, it has a CPU, and it connects to program memory and data memory. This is a hardware architecture where you can see programs, instructions are here separate from data. And it has I/O buses that connects to I/O ports, and also data buses connected to other units, counter, ADC, UART, serial. For I/O ports, this is you can find that this processor has named ports B, C, D, and each port has 8-bit or sometimes 7-bit bidirectional pins. And in this diagram, you can see those are color labeled, but they also have the ports pin or bits name. PD0 is bit 0 of port D. What else? Right, so this is the AVR processor we saw on the previous slide. And you also see those pin names, PB1, PB2 are also labeled here, but it's grayed out. And we have another set of numbers, 9, 10, 11, 12, 13, all these ones. And those are the pin numbers on the Arduino board. Arduino Uno board use AVR processor, ATmel processor, and Arduino board has its own pin numbers. And those pin numbers should not be confused with the actual physical pin numbers on the ATmel on the AVR chip. And many times they're different. Like for example, this 9 is so this is the pin number on Arduino board, and whereas even though it's connected to PB0, but in fact the physical pin number of that chip is pin 14. So just don't be confused with these pin numbers. Okay, for I/O ports, the way to access them is basically using 3 registers. You will find, many other processors, for example, microchip, the PIC microcontrollers use very similar, even name or function. One of the registers is DDR or data direction register, and that register configures its bidirectional pins for either input or output. If it is configured as an input, then we're supposed to read from that pin. So then in that case, you use PIN register to read that. If it is configured as an output, and we're going to use port register to send signals to the outside world. And these are one-to-one mapped. So essentially bit number 7 on DDR corresponds to the bit number 7 on port or on the pin register or PIN register. And for each port, there are 3 such registers. So there'll be DDR-C, port C, PIN-C. Also, there are DDR-D, port D, and PIN-D. Okay, this is the memory map. What's interesting here is that you have, well, first of all, we have this data memory, and on the left side, this is the address range or the address space for data memory, and this is the load address space. So we start from 0 all the way up to 8FF. So we have this large load store address range. And load store address are used by the load store instructions. And that's the way to access these locations. But there's one region from 20 to 5F. If you look at this load store address range, these are 64 IO registers, which can also be accessed using IO instructions. If you use IO instructions, such as in or out instructions, you need to use these addresses. So the IO address range is actually much smaller. It's 0 to 3F. If you use load store instruction, you could use these addresses to access the same IO registers. So that's a unique thing for this processor. It's just, I'll make note of that. And other processors may have similar way to do it. And of course, the address range will be different. So if you look at this, because it's offset 20 corresponds to offset 0, so you can actually translate that address. If you add 20 to this IO address, that gives you the load store address for these 64 IO registers. Okay, so this is the formula you can use to easily translate that between the address ranges. This is just example, a table to show, okay, for these DDRB register, what's the corresponding IO address, because it's 4, so if you use load store address, that will be 24 in hexadecimal. Okay, so this is an example that I talked about in class, and I had one homework question that basically wants you to do a similar design, but using different port. I strongly encourage you to really understand this example. And of course, if you finish the homework question, you know what's involved there. Due to time constraint, I will not go over much detail. But I think the key point is that in this example, we want to use assembly language to program the AVR processor to operate the IO port that we use to drive in this is a button. In the homework, I think it's an LED. So for a button, we're talking about input, right? So we can see here, we have a pull-up. Actually, yeah, we have a button that's connected to a VDD. So, and then in series connects to a resistor, then to ground. And the connection, we use this Arduino pin 12 as a input signal coming from the resistor. So if the button is not pressed, there will be no current, so there's no voltage drop. So this will be a 0 volt, and that's logic low that's supposed to be read into. When you press the button, because this current will go through, and essentially we have a VDD, a logic high to the input. So because it's pin 12 on the Arduino board, so we can look at this one, pin 12, that corresponds to PB4 of this AVR chip. So that means we're going to be using PB4 as an input. Let's see how we're doing that. Well, actually, we should refer to this table. We're using PB4 port bit 4 of port B. So we're going to be using this these two registers. DDRB is to control the direction. PINB is for input, right? Because we're reading the value. So what we do here is we're going to clear R1, which is a general purpose register. We send R1 to this address 4 using IO instruction. and this corresponds to DDRB register. So we're basically putting 0 to this DDRB register to configure port B as output on every single pin, although we only use PB4. And then we use in instruction to read that, to read this register 3, which corresponds to PINB, and then we will do an AND operation to look at bit number 4 of that value, which we read from port B, bit 4. Okay, so that's an example of that. Timer and counter are widely used in these embedded registers to generate any functions related to timing, for delays or for periodic triggers. So you use, again, a combination of these registers to control the mode of counting, and either there'll be pre-scaling or not, the scaling factor and the initial value. So this example of calculating the pre-scaling factor, should we use or not? Because the frequency of the clock is 16 megahertz. So each clock represents about 62.5 nanosecond. If we want to use if we don't use any pre-scaling, that means for the counters to count up to 256, then we only count about 60 microseconds. If we want more of that, so we're going to have to scale the factor, basically let the counter go slower when you have this pre-scaling factor. In that way, we can choose to use this combination so that we choose scale the clock slower by 1024 times. So that will give us approximately 16 milliseconds. Okay, interrupts. Interrupts are the rule. I mean, there are a lot of things happening in the embedded world. As you notice that in your lab 2 and lab 3 design, with interrupts, you can accomplish a lot of things. But at the same time, if you don't program well, if you put wrong things in your interrupt service routine, you're going to be dealing with a lot of weird problems. As you want to describe. For example, your LCD's display is way off, garbage characters, and when you add your motor, suddenly your time doesn't count anymore. So those are all related to improper use or lack of use of interrupts. Okay, so let's see. Yeah, we talk about these different interrupts, and we, I think, showed you some example pin change interrupt. Okay, I think these are pretty much, detailed explanation I included, so I will not go through every single detail. And it's close to 9 o'clock. Let's see. All right, any questions regarding the AVR processor? You may want to ask, are there any programming questions? I'm pretty sure there will be something similar to the homework question. So that's why I want you to review the example in this part of the slide, and also make sure that you understand the homework question and be able to solve it. What else? I think that's all I want to talk about. Did I miss anything? anyone has any questions? Okay, no questions. That's a good sign, or too much information. I mean, it's hard for me and also, of course, for you guys too, to go through these 4 plus weeks of topic within just 2 hours. So a lot of the effort, I think, is on you to review the materials, especially, I think, if you listened, if you attended the lectures and if you listened the topics I covered, you're good on the the lecture slides. But I still encourage you to go spend some time on the textbook materials. I'm not asking you to read the whole book. I specifically list out the chapters, even page numbers. Yeah, not page numbers, but specific chapter and section numbers. So you should spend a few hours on those, get yourself familiar with the content. And as I said at the beginning, that the format of the exam will be same as the midterm exam. There will be still a couple of more questions, maybe. I have not, fixed the questions yet, but it will not be significantly more questions. Oh, I didn't talk about lab 2 and lab 3, but you just finished lab 3, so it's very fresh. For lab 2, I think I suggest you go back to revisit, especially for the people who work in a team. If you only focused on one aspect of the lab design, you want to ask your team members to make sure that you understand the whole thing. I think that's what I want to say about lab 2 and lab 3. Yeah, if you want to submit any assignments that you haven't submit, we can still accept up to this Friday. But just understand that there will be late penalties applied to late submissions. But you have a chance to submit your late work. Okay, so I think that's all I want to cover today. So for next week, we don't have class. This is the final class, and the exam again. Just a reminder, it's on Saturday, December the 17th, from 6:30 to 8:30, 2 hours. So with that, I will. Oh, I have to remind you one more thing about the course evaluation. I will post the course evaluation form on Blackboard because we're doing this course virtual, so there's no way for me to collect the evaluation form. So you have 2 options. You can bring the form, once you fill out, bring the form to the department office, Ball Hall 301, give it to the secretary there, or you can email to the secretary. Just don't give it to me, okay? Either paper or email, don't send it to me. The evaluation will be anonymous, and I encourage you to fill out the form. And I will put detailed instruction on Blackboard in one of the announcements. Okay, so that's all for tonight, and hope you the best of luck in your final exams, all your other courses, and we'll see each other in 10 days on December the 17th. Thank you all. Have a good night.
Thank you.
Thanks, Professor.
Thank you.
Thank you, Professor.